So we continue with our discussion of CNNs. So as we said earlier, there will be then D kernels, not just one as we did in this example, with a stride of 1, and the output will be D times larger. This means that a two-dimensional input array becomes a three-dimensional array of hidden units, where the third dimension is of size D. It's important to organize the hidden layers this way so that all the kernel outputs from a particular image location stay associated with that location. So CNNs were inspired originally by models of the visual cortex proposed in neuroscience, and we will talk more about this later when we revisit computer vision. In these models, the receptive field of a neuron is the portion of the sensory input that can affect this neuron's activation. So in a convolution neural network, the receptive field of a unit in the first hidden layer is small, which is essentially just the size of the kernel, which is L pixels. In the deeper layers of the network, it can be much larger because, as you saw here, the deeper you go into the network, each unit then collects information from the previous layers, which itself allows it to combine information from many more inputs. So in this example right there, a unit in the second hidden layer whose receptive field contains 5 pixels. Okay, you can count them. So for this unit right here, in the second hidden layer, it has the receptive field of these 5 pixels. Okay, instead of just it's not just based on the 3 units from the previous hidden layer, but the entire input vector. So when the stride is 1, like we did in that example, a node in layer M will have a receptive field of size L minus 1 times M plus 1. So the growth is linear in M. When the stride is bigger than 1, each pixel in layer M represents S pixels in layer M minus 1. So essentially what you will see is that the receptive field grows exponentially, okay, as the stride increases. So we learned about the kernel. The second characteristic of convolution neural network is a pooling layer. So a pooling layer in a neural network summarizes a set of adjacent units from the preceding layer with a single value. So pooling works just like a convolution layer with a kernel size L and stride S, but the operation that is applied is fixed rather than learned. So here we don't learn weights in the pooling layer. There's no weights to learn. Instead, we fix the operation saying, for example, we're going to take the average over all the elements of the pooling layer, and that would be the output. So typically then no activation function is needed for a pooling layer. And there are 2 forms of pooling layers. There's a pooling and downsampling. So average pooling computes the average values of its L inputs. So as you can see, there's nothing to learn here. We just have L inputs. We just take their average and that becomes the output. So this is identical to convolution with a uniform kernel vector, where each element of that vector is just 1 over L. And if we set L equal to the stride, okay, the effect then is to make the resolution of the image coarser. So essentially, we're downsampling by a factor of S. Okay, so we could be starting with an image that's very accurate, and then what we're doing here is we're downsampling it. We're taking the average of a bunch of pixels next to each other, and we're combining them into one value. So we're making the image coarser, essentially. The same learned classifiers that would be able to recognize the object in the pooled image, even if it was too big to recognize in the original image. So in other words, average pooling makes it easier to do what we call multiscalar recognition, because it reduces the number of weights required in subsequent layers as well, because we're reducing the size of the problem, leading to a lower computational cost and even faster learning. Another way to do pooling instead of taking the average is to take max. Okay, so max pooling essentially calculates the maximum value over its L inputs, and that becomes the output. So it could also be used just for downsampling, where we take just the max. So if we look at the example we did here, so we have, for example, 5, 9, and 4. If we did max pooling, then the output would be 9, okay, which would indicate that somewhere in the input image there is a darker dot that is detected by the kernel. So in other words, max pooling acts as a kind of logical disjunction, saying that a feature exists somewhere in the unit's receptive field. Now, if the goal is to classify the image into one of a number of categories, then typically the final layer of the network will just be softmax with C output units, depending on how many classes C. The early layers of the neural network will be image sized before we do any pooling. So somewhere in between, there must be significant reduction in layer size once we start applying pooling and downsampling. Convolutional layers and pooling layers with stride larger than 1 all help to reduce the layer size. It's also possible to reduce the layer size simply by having a fully connected layer with fewer units than the preceding layer. So if we don't want to use any pooling, we can just use a smaller layer and make it fully connected. So convolutional neural network often have 1 or 2 such layers just before we reach the final softmax layer. Now let's look at the actual implementation of all of this, which is essentially is done using tensors and tensors operations. So like we saw earlier in the previous slide, applying kernels and pooling essentially could be done using matrix multiplication. Same as gradient descent and backpropagation. Okay, we saw that last week. So vectors and matrices are one-dimensional and two-dimensional special cases of something called tensors, which in deep learning textbooks are simply multidimensional arrays of any dimension. So for convolution neural networks, tensors are a way of keeping track of the shape of the data as it propagates through the layers of the network, through the dimensions of the tensors, essentially. This is important because the whole notion of convolution depends on the idea of adjacency. So adjacent data elements are assumed to be related somehow. So it makes sense to apply operators to local regions of the data. Furthermore, the layers themselves can be described as maps from tensor inputs to tensor outputs. Okay, so we can just think of the layers then as just mapping from tensor to tensor rather than doing anything else really. It's, of course, the convolution layers that we're talking about. One more reason for describing convolution networks in terms of tensor operation is computational efficiency. So given a description of a network as a sequence of tensor operations, a deep learning software package can generate compiled code that is highly optimized for the underlying computational device. So deep learnings typically run on GPUs or TPUs, which stand for tensor processing units, which make available a high degree of parallelism. So you can the operations are optimized for the actual device that's performing the calculation to take advantage of the ability to do all of these backpropagation steps and matrix multiplications in parallel. For example, one of Google's third generation TPU has a throughput equivalent to about 10 million laptops. So taking advantage of these capabilities is key in training a large convolution neural network on large database of images. Obviously, you can't train such a network on a CPU because it's just not realistic. It's not going to work. So it's common to process not one image at a time, but many images in parallel. Okay, so this also, fits perfectly with our approach so far, which is using stochastic gradient algorithm, because we can run mini batches in parallel, right? We don't have to wait to finish one mini batch in order to start the calculation on the next set of training examples. So if we put all of this together, in an example, so suppose we're training on an image, a set of images 256 by 256 with a mini batch size of 64 image. So the input in this case will be a 4-dimensional tensor. So 256 by 256 is the number of pixels, and each pixel has 3 variables, which has RGB, so times 3, and then we set a mini batch of 64 image, so times 64. Then we apply 96 kernels of size 5 by 5 by 3 with a stride of 2 in both x and y directions to the image. So this gives an output tensor then of size 128 by 128. So the 256 get cut by the stride, which is 2. So we get 128, 128 by 96 by 64. Okay, so this tensor is usually called the feature map, since it shows how each feature extracted by kernel appears across the entire image. And with the 96 is called the number of channels in this case, because each channel carries information from one feature in the original image. So note that unlike the input tensor, this feature map no longer has dedicated colored channels, so we don't know what's R or G or B in that case. However, the color information is still present in some way or another. And if the learning algorithm finds color to be useful for the final prediction of the network, definitely the weights for these features will be non-zero. Okay, let's continue the next.